You are about to step into a mystery where science meets the unknown. Imagine a quiet room in a sealed box on the table, large enough to hold a cat and a secret. Inside, in the mind's eye, you picture a delicate glass vial of poison, a Geiger counter listening for a single radioactive whisper, and a hammer suspended like a verdict waiting to fall. The cat pads around in the darkness, unaware that its fate is bound to an atom's coin flip. Minutes pass. Outside the box, there is silence. Inside the mathematics, there is noise of a very strange kind. If the atom is governed by quantum rules, able to occupy a superposition of decayed and not decayed, then the whole contraption, so the story goes, should be able to wind itself into a superposition too. Hammer fallen and hammer not, vial smashed and vial intact, cat dead and cat alive, all at once. How could that be anything but absurd? And yet, when we open the lid, we never see a ghostly blend of outcomes. We see a cat that is either fine or gone. Somewhere between the atom and the animal, something happens to possibilities. What is that something? And where does it live? In physics, in information, or in us? And if you'd like to help me bring more of these mysteries to life, don't forget to like, comment, and subscribe. Tonight we follow a paradox that refuses to die. Schrödinger's cat. A thought experiment that still claws at the boundary between the quantum and the everyday, and asks whether reality needs an observer to decide. The cat was born on paper in 1935, when the Austrian physicist Erwin Schrödinger, one of quantum theory's founders, wrote a short essay in response to a different puzzle, the EPR argument posed by Einstein, Podolsky, and Rosen that same year. EPR claimed that quantum mechanics was incomplete because it allowed spooky correlations between distant systems. Schrödinger agreed the spookiness was real and gave it a name: entanglement. Then he pushed the weirdness home with a parable. If the quantum rules that let an atom be in two states at once are universal, he argued, then those rules extend to the apparatus that reads the atom, and to whatever the apparatus affects. Hence the cat. Not as a proposal for animal cruelty, but as a reductio ad absurdum. If your interpretation of quantum mechanics tells you a cat can be both alive and dead, perhaps your interpretation needs work. The proposal provoked the Copenhagen school associated with Niels Bohr and Werner Heisenberg, who insisted that quantum descriptions apply to microscopic systems and that measurement has an irreducibly classical character. Others, like John von Neumann, formalized the measurement chain and asked why it must stop at the human observer. Later, in the 1960s, Eugene Wigner sharpened the knife with Wigner's friend, imagining an observer inside a lab who sees a definite outcome while an outside observer treats the entire lab, including the friend, as a superposed quantum system. The cat's box, it turned out, could be scaled to include us. To grasp the force of the paradox, we need a few building blocks. Quantum theory describes the state of a system with a wave function, a kind of mathematical cloud that encodes the amplitudes for different possibilities. Between measurements, the wave function evolves smoothly and deterministically, according to Schrödinger's equation. When we measure, we do not, in practice, see a fog of outcomes. We see one. Textbooks capture this with the Born rule, which turns amplitudes into probabilities, and a postulate called collapse, which snaps the wave function of the observed result. But collapse is not derived from Schrödinger's equation. It is added on top. That leaves us with a split personality, smooth evolution when no one looks, abrupt update when someone does. The cat dramatizes the tension. If the atom and Geiger counter become entangled, decay correlated with click, no decay with silence. And if that correlation propagates through hammer and vial to the cat's status, then before we open the lid, the full state is a superposition of two macroscopic stories, each internally consistent. The mathematics has no clause that says, "and now stop." Where then does the single outcome come from? One response developed in the late 20th century changes the way we think about this transition without adding a magical collapse. It is called decoherence. Every real system is immersed in an environment. Air molecules, photons, 1,000 little jostling degrees of freedom that constantly measures it in a gentle way by carrying away information about its state. When a quantum system becomes entangled with its environment, the delicate phase relationships that allow interference between different possibilities get smeared out. The overall wave function still contains both branches, but interference between the branches becomes, for all practical purposes, impossible. Think of writing two superimposed stories in wet ink and pressing the paper against a stack. The marks bleed and stain 1,000 pages. You can no longer read the two stories together. You can only read one or the other. Decoherence explains why macroscopic superpositions, cats and chairs in limbo, are not seen. The environment selects pointer states that are robust under monitoring, and it does this at breathtaking speed for big objects. But decoherence alone does not pick a winner. It makes the alternatives non-interfering. It doesn't tell us why we experience just one. That is the measurement problem in its sharpest modern form. From here, the road branches into interpretations and rival theories, each trying to make the cat either perfectly ordinary or meaningfully mysterious. The pragmatic Copenhagen stance says, measurement is a primitive notion. There is a cut between the system and the classical apparatus. And while its exact location can slide, you must ascribe outcomes in classical terms. Its strength is simplicity and long success in the lab. Its weakness is vagueness. Where does the quantum end and the classical begin? If you push the apparatus into the quantum description, the cut moves. If you push the observer in too, it moves again. The cat keeps meowing. Why should physics depend on where we draw a philosophical line? Many worlds, the Everett interpretation, takes a different gamble. Remove collapse. Let Schrödinger's equation rule universally, and accept that measurement is just entanglement. When the atom meets the detector, when the detector meets the cat, when the cat meets your eyes, the universal wave function branches into non-interacting components, each with a definite outcome. Decoherence keeps the branches from talking. Probability becomes a story about expectation across branches. In one branch you meet a living cat. In another you mourn. Both branches exist in the full state, but observers inside a branch experience a single consistent world. The appeal is conceptual economy, no extra rules, and a clear role for decoherence. The price is paid in metaphysics, a reality larger than what any one observer can see, in deep debates about how the usual probability rule emerges, in which decomposition into worlds nature prefers. Objective collapse models, such as GRW, and continuous spontaneous localization change the equations instead. They keep Schrödinger's evolution but add a tiny, random collapse process that is negligible for particles, infrequent for big objects. The result is a real dynamical suppression of macroscopic superpositions. Cats don't linger in limbo because the universe itself jostles wave functions into single outcomes with a small but relentless noise. These models are testable. They predict slight deviations from standard quantum behavior in delicate interference experiments with increasingly massive systems. So far, experiments have not found such deviations, pushing the allowed collapse rate into tighter corners. But the strategy is admirably scientific. Put the cat's fate in the equations and look for the seams. Pilot wave theory, de Broglie-Bohm mechanics, saves definiteness by adding hidden variables. Particles always have precise positions, guided by a wave that evolves by Schrödinger's law. The cat's atoms take definite paths. The superposition lives in the guiding wave. The theory reproduces all standard quantum predictions if the distribution of initial positions matches the Born rule. Its wins are clarity and determinism. Its burdens are explicit non-locality. The guiding equation depends on distant configurations and technical challenges in extending the framework to relativistic quantum fields. Still, for some, it makes the cat purr. There is always a fact of the matter, whether or not we look. Information-centric and relational views take a different tack. Cubism treats the wave function as an agent's catalog of expectations, not a physical field. Collapse is just the update of beliefs when new data arrive. Relational quantum mechanics says states are relative. What is definite for one system relative to another may be indefinite relative to a third. The cat can be in a definite state relative to itself, in the apparatus, while you, outside the box, are in a different relational state until you interact. Consistent histories formalize the idea that physics licenses sets of mutually compatible narratives, coarse-grained sequences of events that never interfere with one another, without singling out one set as the truth. Each of these frameworks softens the paradox by reminding us that state and fact are concepts embedded in a web of relationships and in the questions we ask. Then, there are speculative ideas perched on the boundary between physics and philosophy. Wigner once flirted with the thought that consciousness causes collapse, the mind as the final measuring device. Few physicists accept that today, partly because decoherence and experiment have shown how classicality can emerge without invoking minds, and partly because consciousness is too vague to be a term in an equation. Penrose, in another vein, has suggested that gravity might induce collapse. Perhaps superpositions of very different space-time curvatures are unstable, pushing big objects toward definiteness. This too is being tested in tabletop experiments that try to put small masses into quantum superpositions and watch for anomalous decoherence. Time-symmetric approaches urge us to think of quantum processes as constrained by both past and future boundary conditions. On this view, the mystery is partly our insistence on a one-way narrative in a two-way law. None of these ideas has carried the day, but each forces clarity about what would count as an answer. Outside the armchair, the cat has slipped into the lab in surprising ways. Physicists routinely create Schrödinger cat states in superconducting circuits, where a current can flow clockwise and counterclockwise at once, and in trapped ions and microwave fields where coherent states of motion or light are superposed. Massive molecules, carbon buckyballs and beyond, have shown wave-like interference, pushing superposition up the complexity ladder. Tiny mechanical resonators have been cooled to their ground states and coaxed toward quantum behavior. No one has put a literal cat into a superposition, nor should they. But the trend is clear. The quantum/classical boundary is not a wall. It is a fog that lifts as you learn to shield systems from environmental monitoring. Decoherence provides the weather report. Engineering provides the umbrella. At the human scale, the paradox is less about physics and more about meaning. What is a fact? In our everyday intuition, facts are local and self-contained. The cat is alive, the vase is broken, the email is sent. Quantum mechanics suggests facts can be relational. What can be said about one part of a system depends on how it is correlated with the rest. Before you open the box, there is no single story you can tell that assigns the cat a definite state relative to you without also specifying which records exist in the world. After you open it, there is. That can feel like an affront to common sense, as if reality waits for us to notice it. A calmer reading is that reality is a tapestry of stable patterns, pointer states, that decoherence weaves, and noticing is just the moment you become part of the tapestry.
There is an existential shiver in this too. The cat's box is a mirror. We live with superposed possibilities every day, not in electrons but in plans. Before a choice, many futures coexist in a space of imagination. After a choice, only one future becomes your story. Physics does not need your attention to make an atom decay. The universe is not a choose-your-own-adventure book written for us. But the cat reminds us that what happened is often a question about which records exist and how we bind them into a narrative. In that sense, the measurement problem leaks into the humanities. We are authors of context as much as discoverers of fact. So where does this leave the animal in the box? If you are a Copenhagen loyalist, you say, the paradox exposed a category error. Quantum concepts apply to specific preparations and measurements. The cat is a metaphor stretched too far. If you are an Everettian, you say, the paradox dissolves when you stop amputating branches. There is no single outcome to demand. There are many, each decohered, each as real as the other, and your experience rides one. If you favor objective collapse, you say, the paradox is a clue that the equations are incomplete. Nature herself chooses, with tiny nudges that grow with size. If you carry a pilot wave in your pocket, you say, the cat had a definite pulse all along. The mystery is in the guidance law. If you speak in the language of relations, you say, the cat is definite relative to the apparatus long before you arrive. The paradox is born of mismatched perspectives. And if you are a working experimentalist, you say, tell me which prediction differs, and I'll try to build the device to test it. We often end scientific stories with a triumphal solution. This one ends with a productive truce. We know how to calculate with extraordinary accuracy. We know how and why macroscopic definiteness emerges in practice. We have rival stories about what lies beneath, each with strengths and weaknesses, each suggesting different places to press with future experiments. The cat, in other words, did its job. It forced us to confront that quantum mechanics is not only a set of equations, but a philosophy of what counts as real. As you picture the box one last time, let the scene play twice. In one telling, you open the lid to a sleepy cat and laugh at yourself for worrying. In the other, you feel your stomach drop. Both stories are human. Only one is yours. Physics does not decide which. Life does. The paradox was never about a pet in peril. It was about us. Learning to live with a universe that is lawful, reliable, and stranger than the stories we inherited. So here's my question for you, and I hope you'll wrestle with it in the comments. If you had to choose, not just as a matter of taste, but as a guide for future experiments, where would you place the line between possibility and fact? On the atom? On the apparatus? On decoherence? On us? Or would you erase the line entirely and let the wave function be the only script?